So I'm going to take an example from the textbook to show you how a decoder would overcome the errors in a system. So this is based on that first decoder that I built. I assumed that I had a certain received sequence, and I introduced all of the branch metrics. And from those branch metrics, how do we get to the situation where we had two choices? I gave you something very simple. Here's two paths. But how do we get to that point? Well, we do it systematically, step by step. I assume I started at state A. I could have gone to state A or gone down to state B. I calculate the branch metrics, and the path metrics are the same thing here. It's easy. Next case also. Now there are 4 possible states at the end of time 3, but again, each one of them only has one possible path coming into them, so there's no ambiguity here. And again, I can calculate what are the path metrics. If I arrive here, it's going to be 2 plus 1, it gives me 3. So I can build my path metrics for this case. Now I get to where things start getting interesting, because now when I get to time 4, now I've got 2 paths coming into each one of the states. So I'm going to have 2 candidate paths on each one of the states. And so I'm going to have to do this evaluation of the path metric to choose what is the surviving path. So I go through and I focus now on one endpoint. You know, sure, I've got 4 states I have to address, but let's just look at the first one. Where does this come from? Is it the one that came from above or the one that came from below that got me to this path if at time 4 I really am at state A? So along the upper path, I calculate a path metric of 4, and along the lower path, I have a path metric of 3. Okay, so I compare 4 and 3, and I say 3 is smaller. So I prune my path. What I mean by prune my path is this part of the transition I get rid of entirely. It's like it didn't exist. So when I look here at my survive path, there's just one that I keep. The other ones I get rid of. Now I did that for the first one. The losing path is removed. We take the gardening analogy again. It's a trellis, it's a garden. I'm pruning, I'm cutting out the part that I don't need. Now I go down to the next state. Now I just go down to B. Now I just ask the same questions. To get to B, did I come from the lower path or the upper path? And so I calculate the distances for each one. Upper path, distance 4, lower path, distance 3. Once again, I choose the lower path. And so once again, I eliminate the path that lost. I prune it away. And so you'll see that coming into here, there's nothing there from that path. I go down to the next one. Oh, let's go back. Okay, one interesting point is, if I look back at my pruned paths, I didn't go through all of the examples, but leave that as an exercise. You can do the same calculations for C and D, and you will get this result. These are the pruned paths going up to time 4. So having gotten to time 4, with these 4 possible paths, what conclusions can I draw from having reached this point? So the first thing I want you to observe is that all 4 of these paths have a common element here between time 1 and time 2. This transition everybody agrees with. Whether at time 4 I think I'm at state A or I think I'm at state D, I am sure that when I was here at this transition was a 0. We call that a merge. And at a merge, that means that I can output a decision. When I get a merge, I don't know at time 4 which one of these maybe I'm at. But I know that at time 1 what it was. So now I can output this from my decoder, and I can continue on until I get another merge where I can kick one out and make decisions. So there's a delay involved in doing the decoding process because I have to see the dependencies develop with time. And as I see the development with time, there's going to be some natural decisions which are kicked out. Now, sometimes I can't tolerate too much delay, or maybe this delay will go on forever. The other thing is I have memory, and I have to save all of these paths as I step through time. And maybe I have a finite amount of memory. And after a certain amount of time, even if there's not a merge, maybe I have to make a decision anyway. So I run out of memory, and I have to decide, which of these two are going to be the decision. So then what I would do is look at the paths and see which one's more likely. But for now, the idea is that there's a certain length that as a designer I can say. There's a certain what we call a traceback length. And after that traceback length is exceeded, I'm running out of memory. I have to make a decision now because I can't keep this old part of the paths. So we can make this as a compromise. We want it to be long enough so that we won't have to force merge very often, or when we do force it, it will be so deep back that it's going to be pretty obvious what it should be. Or we have to tolerate the added memory requirement. But anyway, engineering choice, traceback length. So let's continue in our example just to hit a place where things become a little ambiguous. For instance, now let's say I'm looking at state B at time 5. Well, first of all, there is some efficiency that I can use in the algorithm. For one thing, when I get to this point, and I'm looking at the upper path, I don't have to look at 1 plus 1 plus 2 plus 0 and do the whole calculation of the whole path metric again. What I do in my algorithm is, when I get to a certain point, I've already calculated the length of the path. I saved that. In memory, I put two things. For state A at time 4, the path was this, and secondly, the length of the path was 3. So I start thinking about what is it in the complexity of this decoder. Well, the complexity of the decoder is each one of the states, I have to keep the path that got there. I always have, 4 paths, one for each one of the states. So that's a sequence of bits, and the length of that sequence is the traceback length that I said. And I also have to keep the path metric. So why is it good to keep the path metric? Because now, in the next interval of time, I don't have to go back and recalculate it. The upper path at T5 comes from T4. And so T4, the path up to that point at state A, was 3. And so I just add 3 and 1, and I get 4. The lower path came from state C, which had length of 0. And from that, I can see that the total length now is 1. I'm sorry, I was pointing at state A, and I should have been talking about state B, my mistake. So state B, the upper path, also came from state A. Sorry about that. So I'm at state B, I'm wondering about the two paths, and I say, well, the upper path came from state A. State A had a path length of 3. Now the transition from A to B has a branch metric of 1. So the new path metric will be the sum of the old path metric plus 1, which gives me 4. The lower path came from state C. So I look at state C, what the length was. It was 0. I add 1, I get 1. So now I don't have to go through and do the entire path length calculation. I just need the delta. Previous path metric plus new branch metric gives me new path metric. And again, I compare 4 and 1. Clearly, the lower one is smaller. I keep the lower one, and I prune out the higher one. Now let's look what happens on this particular example when we're looking at state C at time 5. And at state C, we have two possibilities. The upper path has a branch metric of 0. The lower path has a branch metric of 1. And the upper path came from state B. The lower path, we're going to do the lower path first. The lower path came from state D, and it had a length of 2, and I'm adding 1 to it, it gives me 3. If I look at the upper path, it came from state B, and that had a length of 3, and now I add 0 as my branch metric, I get 3 and 3. Okay, now what do I do? Well, they're both the same. Which one do I keep? Completely arbitrary choice. Take a coin and flip it. Doesn't matter. Later on, it won't be better. You're always going to say they're both equal length. It will never be useful to you to keep those two paths because you will never be able to choose between them. So since you will never know how to choose between them, you just make the decision up front, toss a coin, keep one of them, and move on. So that brings us to the end of time 6. You can go through and do the calculations as you wish, and you will find yourself at this final point at time 6, where you have, again, always 4 candidate paths. If we look backwards, there's 2 paths that everybody agrees on. And then what we have now are some path metrics. So each one of those different paths has some associated number of errors. So if I ended up at state A, it's because there were 2 errors. If I arrive at state B, I assume there are 2 errors, etc. And if I arrive at state D, it would have been because there was 1 error. So if I had to make a decision, if I was forced now to make a decision on what path is the most likely path, I would choose the path with the smallest path metric. And I would go back here and choose that path as the final path, if you were forced. So let's now look at the complexity. What is it that this Viterbi algorithm, why is it useful? Because we have taken what would otherwise be a brute force search, all of the possible paths, and instead we have created a sequence of operations that organizes and does it in an orderly and efficient manner. First of all, what operations are we talking about? Well, they're extremely simple operations. In fact, there are 3 operations: add, compare, select. Add, take the previous path metric, add to it the branch metric. I did my addition. I always have 2 for each one of the states. I compare the 2. And the one that's the biggest, I get rid of it. And the one that's the smallest, I select it. And then I know to move on. Add, compare, select. So these are the operations that you require in your hardware. Very, very simple. Memory. So this comes to the traceback length, the maximum length of a path, or the traceback length. And that, like I said, is an engineering choice. And it forces me to create a merge maybe when there isn't, to force a convergence when there isn't. And there are some good figures of merit for what would be a reasonable length, a good compromise between complexity, the size of the memory, and the performance. And it's something like 4 or 5 times the constraint length of the code. So the longer the constraint length, the more powerful the code, because you can imagine you have more redundancy, more interconnectivity that gives you more structure to your redundancy. But of course it also increases the complexity of the encoder because you have more registers, minor increase in complexity, but a big increase in memory also in the decoder. So memory can be characterized by this traceback length, this maximum length of a path that you're going to keep track of. And then you have to ask yourself, what are the elements that are being kept in memory? And part of them is the actual state. You know, I need a bit sequence for each path. So there are 2 to the k minus 1 is the number of states. Okay, and for each one of the states, I have to keep a bit sequence. So each one of the states, I have the path leading to that state. And so h is the length of that path. And so this is the number of memory cells I need that just keeps the paths. Now, in addition to the paths themselves, for each one of the states, I also need to keep the path metric. So maybe this is binary memory, and this is, I'm going to have several bits, you know, allow me to accumulate the path metric. So, operations, what are the complexity for the Viterbi algorithm, and memory? How much memory do I need to keep? One way to quantify the quality of a code, so suppose I have offered to me a selection of codes. Which code should I use? Or when I'm designing a code, how do I know if I've gotten the best code that I can for a given level of complexity and redundancy, or if there were a better set of vectors? So the way that we can evaluate code is to talk about the distance between code words. This is an important concept that helps us understand why error correcting codes work. I like to talk about original message space. A message originally had k bits, and we move it to n bits. If we look at the possibility of all messages, it's the size of 2 to the k. But if we look at the space of all code words, there are 2 to the n. Of course, 2 to the n is much bigger than 2 to the k because we choose, we've added redundancy. So think of this as a space, some sort of space, and this is the dimension of the space. So I started out with a space where it was big enough to have 2 to the k messages. And that's all the space there was. There was space in this set for 2 to the k messages, that's it. Now I've expanded it, and I have a much bigger space. And in this bigger space, I still only have 2 to the k messages, because the other ones are not valid code words. There are valid 2 to the k code words. So this big space has space for 2 to the n words, but there are only 2 to the k of them, which actually represent valid code words. These things are now, they've got emptiness around them. And the emptiness around them is kind of what makes it more robust. It's easy for me to tell which one of these code words is right than it is to tell me which one of these messages are right, because these messages are fairly close, but these code words are far apart. So if you think of it in an abstract way like that, you can think about these code words being placed in space. And how far apart these code words are tells me how good these code words are. A good code is going to have code words that are far apart from one another. A really bad code is going to have like 2 code words right next to each other. That would be like useless, because the whole point of creating this big space was to be able to spread things out. All of this is motivation for the quantification of the quality of an error correcting code. And the quality of an error correcting code is determined by the distance between code words. So there's this big space. How far apart are they? In different codes, they'll have different minimum separation between code words. So I said at the beginning that there were 2 kinds of codes. There were block codes, convolutional codes. Block codes are a little more straightforward. This whole thing I said about 2 to the n dimensional space, it's like, really is that? But now when I'm talking about convolutional codes, it's really sequences that are a code word, right? Block codes, K becomes N, it's a set of code words, that's it. Convolutional codes is really a little more complicated than that because there are sequences. But really, I can also define a distance between sequences. I've already done it, these path metrics, So I know how to define a distance between code words in a convolutional code. And they are going to tell me whether I have a good code, a great code, a lousy code. So what we want to do is, among all of the typical, all the available valid code words, look at all of the pairs and find out which ones are at the minimal distance. And the ones at the minimal distance that determines the strength of the code, just like it is with a constellation. Same goes for the code. Except now these code words are going to be sequences. So they're going to be paths. So I have to look at any 2 paths through the trellis and look at the 2 paths which are the closest, and they will determine the minimum distance for my code. So there's a trick when I'm trying to find this minimum distance. So we can think of it as 2 candidate pairs. So I have a sequence which is bit 1, bit 2, bit n. Here's some sequence through the trellis. And then I have another one, some other sequence through the trellis, some other path through the trellis. And I'm saying, what is the distance between these 2? And I want to do this for all of the paths that are possible through the trellis, all of the pairs. Calculate the distance between them. Hamming distance for hard decisions. But there's a little trick, and that is because I realize that this is a linear code. And linear codes, all I have to do is compare the distance between any one of these code words and 0. And when I find the minimal distance between this one and 0, it's the same as if I had checked them all against one another. Okay, so it's just a trick. So if I want to find the minimum distance, what I do is I check all of the paths, and I say, how far is this path from this code, and that tells me the distance, and I try all the bonds, and the one is the smallest. Well, I know if I checked all of the pairs, I'd get the same thing. So now that we've seen the concept of the minimum distance for a code, let's go through the mechanics. How do I find the minimum distance for a code? So, procedure is quite simple. I start at state A, and I finish at state A. Why do I start at state A and finish at state A? Because my whole point was I was going to compare it to a path that was all zeros. And the path of all zeros is state A, state A, state A, state A. So it starts at A and it ends at A for sure. So now I look at all the paths. They could start at A, end at A, and they can do anything in between. So I check all of those, and I look for the smallest distance. And when I find that, all of the possible paths start at A, end at A, whichever one is the shortest distance, that's the minimum distance. We call that, for convolutional codes, instead of calling it the minimum distance, we call it the free distance. And the free distance of a code determines the performance of that code. In fact, the minimum distance, this free distance, actually tells us what is the code's ability to correct an erroneous path. And that is, I take the free distance, minus 1, divide by 2, take the greatest integer, and that is the maximum number of bits I can correct. And of course, the larger this number is, the more errors along the path that I can fix. Remember I said that the path length was the number of errors? So how many errors can I correct? Up to a certain amount. After that, my redundancy is not sufficient. I'm not going to be able to correct it. So clearly, I want to have the free distance as large as possible. I want to correct as many errors as possible. So let's start with our example and start looking at distances for different paths. So the first way is I just have to start at A and end at A. And so I just start looking through the path. Well, I can start at A and go down to B. I'm at B. I eventually want to get back up to A, so I'm not going to go down to D. I'm going to say I go back to C. Oh, from C, I have a path that lets me up to A. So there's one path, and I just chose it just like that. I started A, I ended A. And I look now at the difference in the decoder, supposing that the true code word was the 00, because state A to state A is always 0 code word. I look at the code word for transition A to B, and I say how different is it from the code word 00. And the code word for the transition A to B is 11, so the distance is 2. So now I look at the transition from B to C, the code word, and I take the code word, the difference between that and the code word for A to A, which is 00, and there's 1 bit, and here there's 2. So now I add these up, 2 plus 1 plus 2, and I see that that path has a path length of 5. Okay, so that's 1. Now I gotta do all the paths that start at A and end at A. So I went to B and I went to C. Now suppose instead of going to C, I went to D. Well, I got to D and I said, I'm trying to get up to A, so I'm going to go to C, and then I'm going to go to A. So now I have the path, and I can calculate that metric. It's okay. Let's look at another path. Suppose that I stayed at D instead of going to C, and now I see that this is 7. So I had a 5, a 6, and a 7. It's getting bigger. So now I get, I know that if I start adding segments here, it's just going to get bigger because I'm sort of doing all of the variations on how to get back up to A. So I go through that exercise. Here's one I just want to point out where this path seems longer in time, but it's only length 6. So you really have to investigate all of them, depending on the code, to see which one has the shortest length. But you go through the exercise up and down, calculating each time what is the distance. And finally, when you do that, you find the one that was the smallest, and that determines the efficiency of your code. And in this case, the free distance is equal to 5 for the code that we've been using in our example. If we go back now, if I say that the free distance is equal to 5, that means that that I have 5 minus 1 divided by 2, 4 divided by 2 is 2, greatest integer in 2 is 2. So this code can correct errors up to 2 errors in the code, and the path, excuse me.